Hello and welcome to this lecture on receptors as drug targets. We'll spend the first 10 slides reviewing some of the concepts about receptors and messenger interactions that we've looked at in previous lectures. And then we will jump into a conversation on agonists, antagonists, inverse agonists, and some of the requirements to synthesize or to design those molecules. So let's jump right into that brief review here. So as we've seen a few times before, the way the receptor function is that it has a binding site that's going to interact with a messenger. Oftentimes this happens on the outer layer of the cell membrane. And so once a receptor binds to, once a messenger binds to the receptor, it's going to induce a change in the conformational um, arrangement of the receptor, which is going to lead to a series of events inside of the cell to cause um, signal amplification. Okay. Now, as we as we've looked, the signal amplification uh, uses second messengers, and we've looked at some of the second messengers in detail. At the end of the in order to end the process, the messenger then is going to um, the binding interaction between the messenger and the receptors are going to be disrupted, causing the messenger to leave the binding site and um, stopping the interaction between the receptor and the messenger. And so so those binding sites either hollow or are in the receptor or in a cleft in the receptor surface, and they're recognized by specific chemical messenger. Every receptor has specific chemical messenger that they bind to. This is the case because the messenger and the receptor have to be involved in intramolecular bonding. So the ability of the site to recognize the chemical messenger really is the ability of the functional groups on the messenger and the receptor to interact with each other. Okay, so the binding leads to an induced fit, which changes the receptor shape, which then leads to the release of second messenger and signal amplification. Okay, now when the signal amplification or signal transduction happens, it releases a message, a signal that's received inside of the cell, and then that messenger or that message is going to cause different reactions within the cell. So we've seen this with um, kinase receptors. We've seen this with ion channels and other types of receptors. Now, once the receptor moves or departs from the binding site, then the effect stops and the receptor goes back to resting phase. So once the messenger departs, the effect stops and the receptor goes back to resting phase. Now, when we look at the receptor binding site, again, it's very similar to what we looked at with the enzymes. That binding site can interact with chemical messengers. It contains amino acids, and the messenger is not transformed or changed. It binds. There's no catalysis that takes place. It binds and then it is released. And this is an image of the binding site, um, and and this is where the messenger is going to be able to bind to. Now, the messenger binding, when it occurs, is going to lead to an induced fit, and the the binding site has nearly the correct shape. On approach, when the messenger approaches the binding site, is going to cause the binding site to change its shape to accommodate that messenger. And as a result of the change in the shape, there are other sites that are going to be open. There's other um, There are other allosteric sites that are going to be open. There's other active sites that are going to be open to allow the receptor um, to perform signal transduction. Now the bonding forces, we've already looked at them. They're the ionic, H bonding, van der Waals. You're very familiar with that. So if we look at this hypothetical binding site and this hypothetical, inside of this hypothetical binding site, you have phenylalanine, you have a serine, aspartic acid. All these have these amino acids that can interact with a molecule and interact with van der Waals interactions. You can have ionic interactions here. You can have hydrogen bonding interactions here. Now, when those bonds are initiated, then it's going to lead to a induced fit inside of the molecule. Now, the induced fit is there to maximize the intermolecular bonding interactions. Okay, so at the beginning, when the messenger gets in, the intermolecular bonds may not have the optimal length. The chemical messenger may not be oriented the proper way, but when it begins to interact with the amino acids that are present inside of the binding pocket, then it rearranges, and not only does the receptor rearrange, but it rearranges because of the bonding interactions are going to cause it to fit the messenger in a way that maximizes those bonding interactions. Again, this is still review. Messenger comes, binds to the receptor, causes an induced fit, leads to signal transduction, and then the messenger leaves. Okay. You need to have a certain balance between the interaction, the binding of the messenger, and the strength of the binding interaction, and also how long the messenger remains inside of that receptor. It needs to stay long enough in order to have signal transduction. The binding interactions have to be strong enough to hold it there, but they have to be weak enough to also release the messenger and allow it to depart. So there is a certain balance when it comes to binding interactions there. As a general rule, those messengers tend to bind and quickly depart. In the biological world, what we call quickly here leads to the release of hundreds of signals, hundreds of second messengers that are going to lead to signal transduction and signal amplification. Okay, so agonists are designed to mimic the natural messenger. Okay, so the agonists are designed to mimic the natural messenger. The agonists bind quickly and are also able to leave quickly. The number of binding interaction is very important when it comes to agonists. Now, when it comes to antagonists, antagonists are designed to block the natural messenger. So they come in, they bind at the binding pocket and block the natural messenger. Antagonists seem to have stronger and more binding interactions. And oftentimes the binding interaction can result from a different type of induced fit than the induced fit from the agonist. Okay, so they bind in such a way that the receptor is not activated. So remember, the messenger binds, the agonist or the endogenous ligand is going to bind, causing a conformational change that in many cases is going to lead to the opening of an active site or the opening of another binding site that's then going to bind a different molecule. In this case, when the antagonist binds, the induced fit is different. So that binding cleft that was supposed to be open will not be open, and so the receptor will not be activated. So let's talk about design of the agonist. So the agonists, as we've said, are going to mimic the messenger of the receptor. They're going to mimic the endogenous messenger, and they bind reversibly to the binding site. And this is important to mention here. They bind reversibly to the binding site, and they're going to produce the same induced fit as a natural messenger. A receptor is activated. Now, although they produce the same induced fit, their effect can be stronger than the actual natural messenger. or they can be at the same level as the natural messenger. Similar intermolecular bonds are formed as with a natural messenger, and they're often similar in structure to that natural messenger. Now, if they're not similar in structure, they at least have the functional groups that can interact with the same types of binding region that the natural messenger would have bound to. And this is an image that we've used often in this class here about how the agonist comes in and binds. So it really mimics what the endogenous ligand would have done. So some of the requirements, it has to have the correct binding groups. Not only does it have to have the correct binding groups, the binding groups needs to be positioned correctly to interact with the binding regions. And the drug has to have the proper shape and proper size. Not only the proper shape, but also the proper size. Okay. So let's say you have this hypothetical messenger here and receptor. So looking at this drug here, you're already looking at potential interactions. You know, you have probably going to have some pi stacking, van der Waal interaction. Going to have some hydrogen bonding interactions here. Probably have ionic interactions here. So this particular neurotransmitter has the binding groups here, and these are the different regions in the receptor that we're going to be looking at. Okay, so van der Waal binding region there, hydrogen bonding region here, and then ionic binding region there. So that hypothetical messenger is going to fit within this this binding site. And as we mentioned, you have the van der Waal interactions taking place here. Okay, taking place here. You have the hydrogen bonding taking place here, and then you have the ionic interactions in here. Now, after the interactions are initiated, then you have an induced fit to maximize bond length, and also orientation. Okay. So that induced fit is going to allow for stronger binding interactions. As we keep looking at the design of agonists, we mentioned it needs to have the correct binding groups. Okay, so in the case of this hypothetical neurotransmitter here, you have a hydrogen bonding group there, van der Waals bonding group, and then ionic bonding group. So these possible antagonists are here. As you can see, you maintain the possibility of having the van der Waals interactions. Okay, maintain the H bonding. Okay, and you also maintain the ionic bonding group here. So those are possible binding. Those are possible agonists. Possible agonists. So the identity of these binding interactions is important, and these agonists are designed to have functional groups that are capable of the same interactions, and usually they require the same number of interactions. Sometimes you have to identify the binding interactions that are actually essential for activity and have those binding interactions present with the agonist. So for these two molecules here, let's look at first of all this one here coming in, number one here coming into the binding site. So we can still have some van der Waal interaction, but not as much as we would have with this ring here. Okay, and when you compare it with that, you actually have more of the binding interactions here. Now you also don't have, in this case here, you don't have the ionic interaction that would have happened here. In this case, you have the positive charge and the negative charge, so you have an ionic interaction taking place. One more thing that's missing, you don't have the hydrogen bonding interaction that would have happened here. Okay, so you are missing some of the groups that were present in the other analogs. Okay, so structure 1 has one weak binding group, has negligible activity. Structure 2 has two of the required 3, and also has weak activity. So not only do you need to have the correct group, but they need to be positioned correctly. So this particular molecule, for instance, has the ability to engage in van der Waals interactions, the ability to engage in hydrogen bonding interaction, and the ability to engage in ionic interaction. It does have all that, but it can only engage in two interactions because the hydroxyl group here is too far removed from the other hydroxyl group here to engage in hydrogen bonding interaction. So there is no hydrogen bonding interactions there. So this molecule will probably have poor activity. So still looking at correct positioning here of binding groups. Now, if you have a molecule that has activity, the mirror image of that molecule may not necessarily have activity. Actually, is almost, in a lot of cases, will not have activity or similar activity in um, uh, similar activity within that same receptor or that same enzyme. One of the big example here is quinine and quinidine. Quinine is an anti-malarial. Um, Quinidine is an anti-arrhythmic. The difference between those two is their can't remember if they're mirror images, but I know that is the orientation around a particular chiral center. As a kid, I took quinine a lot for malaria. Quinidine is used as an anti-malarial. So they both have the same groups, they're just oriented differently. So in this particular case here with these hypothetical neurotransmitters here, so you see the mirror image. These two are mirror images of each other, the enantiomers of the chiral molecule. So you look at the binding site here. The original molecule will be able to bind and have the three interactions that I needed: the van der Waals, hydrogen bonding, and ionic. Now, when it comes to the enantiomer, it comes in. It can certainly engage in the van der Waals interactions. It can certainly engage in the ionic interaction, but it is not able to engage in the hydrogen bonding interactions here. So the correct position of the binding group is essential for activity. Okay. So two enantiomers can have different biological properties. Now size and shape as well. This molecule here has all the different groups that we need: van der Waals, hydrogen bonding, and ionic. But it's too big. It won't be able to fit within the binding pocket because of the steric block here. It's not going to be able to get in. Okay. There's also another steric block down here. So it's not going to be able to get in. No fit. Okay. So agonists must have the correct size, correct shape to fit the binding sites. And when you have groups that are too big that prevent access, they are called steric shields or steric blocks. All right, now let's deal with allosteric modulators. So these are agents that will enhance the receptor activity by binding to an allosteric binding site rather than the messenger binding site. Example number one, benzodiazepines. They target an allosteric site on the GABA A receptor. And you also have cinacalcet. Cinacalcet is a molecule that's actually used to treat thyroid problems, thyroid disorders. And it's an allosteric modulator for a G protein coupled receptor called the calcium sensing receptor. So these will bind at an allosteric site and enhance receptor activity. All right, so now let's deal with antagonists. Antagonists are groups that are going to bind to the receptor, and they are basically going to block the natural ligand from binding to the receptor. Block the natural messenger from binding to the receptor. These antagonists can bind reversibly to the binding site. So if you increase the concentration of the endogenous messenger, you may be able to remove the antagonist from the binding pocket. There are intermolecular bonds that are involved in binding. So these antagonists may or may not bind stronger to the binding site than the actual messenger. Again, the antagonist come in, it binds to the receptor, okay, it binds to the receptor. Induced fit takes place, okay, there's an induced fit that takes place, but it's different than the induced fit with the messenger, okay, it's different. So it does not lead to receptor activation, okay. In this particular case, the antagonist is not going to undergo a reaction, and as we mentioned before, it depends on the concentration of the antagonist. Okay, the messenger is blocked from the binding site, and if you increase the concentration of the messenger, you can actually reverse the antagonism. So antagonists are going to bind to the binding site, but they fail to produce the correct induced fit. So the receptor is not activated. The normal messenger is blocked and cannot have access to its binding site. So just like we see here, all the interactions are the same, but it is going to have an induced fit that will be different than if it was a messenger. Now, in this particular case here, because we may have studied the structure of the enzyme, we can design a molecule that will have a perfect fit. Because we've studied the structure of the receptor, a molecule that has a perfect fit comes in, binds to it, and so the type of induced fit that will be seen here will be very different than what you will see with a natural messenger. Now, there's some other antagonists that can actually form binding interaction with other binding regions that are not used by the natural messenger. Okay, so there's some extra binding regions here that may not have been used by the chemical messenger, the endogenous messenger, that will be used by the antagonist. Okay, so you have this hypothetical neurotransmitter here and this is the binding site. Okay, you have the binding site. So this hypothetical neurotransmitter, as you're looking at it, you can already see that the positively charged amine here is going to interact with the negatively charged aspartic acid. You have a hydroxyl group here, so there's possibility to interact with hydrogen bonding here. And then you have these hydrophobic pockets here where the aromatic ring can probably interact with the binding region. And so when you look at the way the neurotransmitter will fit in the binding site, it goes in, it starts interacting, and then because of the induced fit, uh, the receptor is going to change its shape to accommodate that particular neurotransmitter, just to make sure that the binding, the bond length is optimized, the orientation of the molecules are also optimized. Now, when you introduce an antagonist, you're still dealing with the same binding pocket, but the antagonist can come in and take advantage of additional binding regions inside of that binding pocket. Okay. Now, the induced fit here will mainly be to maximize the ionic interaction here and the H bonding interaction here, and it's going to lead to an induced fit that's different than what you would have seen with the endogenous neurotransmitter. Now let's deal with irreversible antagonists. Irreversible antagonists basically will have an actual covalent bond with the receptor and bind to that receptor for the lifetime of the receptor. So they're designed to take advantage of the conformation of that receptor. So they're designed with the intermolecular interactions in mind. They come in, they bind to the receptor, but in addition to binding to the receptor binding site, there is some covalent bonding that takes place that leads to the antagonist being bound irreversibly to the receptor. Again, there's a different induced fit, means that the receptor is not going to be activated, and the messenger is still blocked from the binding site. You can increase the messenger concentration. That will not reverse the antagonism. Often these are used to label receptors. So you can have radioactive labels, radioactive molecules come in, bind to the receptor, and um, have a covalent interaction with that receptor, and they stay bound to that receptor. Then you can use those um, radioactively bound receptors. Um, you can use them to identify how much of your compound is actually bound to the receptor. This is an example of propylbenzylcholine mustard, and this moiety here you've seen before as we've looked at um, um, the type of interactions that can take place here. So this particular molecule here, drawn here in a cartoonish representation, can actually go and interact with the binding site where there are nucleophilic groups that are available, and those nucleophilic groups um, are actually going to interact and form covalent bonds so that the antagonist is actually going to be bound to the receptor for the duration of the lifetime of the receptor. Allosteric antagonisms, um, the antagonist is going to bind at a different site, at an allosteric site, and causing a different types of induced fit, which is going to cause the binding pocket to be unrecognizable. Now, the antagonist binds reversibly to the allosteric site, and again, intermolecular bonds are going to be formed. The induced fit is going to alter the shape of the receptor, but it alters it in a way where it's distorted and it's not recognizable by the messenger. So you can increase the concentration of the messenger here again, but it will not reverse the antagonism. Now there's another effect called the umbrella effect, where you have antagonists that bind reversibly to a neighboring site, but the antagonist is so big that it also covers the site where the binding of the messenger would take place. Okay, so it basically overlaps the messenger binding site, and it prevents the messenger from binding to its site. So let's look at it here in picture form. So you have the binding site for the messenger here and the binding site for the antagonist. The antagonist is going to come in and bind, and as you can see, it not only does it bind to its binding site, it also obstructs the binding site of the natural messenger. So now the messenger comes in and it cannot interact with its binding site. Now you have what we call partial agonists. These are agents which act as agonists, but they produce a weaker effect. So they go in, they bind, they have interactions, but the effect is not as pronounced as the actual agonist. They have all the interactions that you can think of. It's just not as strong. It's just not as strong. So for instance here, if we were looking at a channel, like an ion channel, for instance, you can have the receptor binding to its messenger, causing a partial opening of the ion channel. Okay, not a complete, but a partial opening. So this agent does not produce the ideal induced fit for maximum effect. It could be that those agents combine in two different modes, one where the agent acts as an agonist and one where it acts as an antagonist, and then you basically have to balance out the effect between the agonist effect and the antagonist effect. Okay, and another way you can think about it is that the agent binds as an agonist to one receptor subtype and as an antagonist to the other receptor subtype. Again, in this case, you will have to balance out the agonistic effect versus the antagonistic effect. Now, inverse agonists are different. They have some shared properties with antagonists in that they bind to the receptor site, they cause a different induced fit from the normal messenger, but the receptor is not activated. They also lead to the normal messenger being blocked. Some of the properties that are shared with the antagonist is the fact that some of the properties that are not shared with the antagonist is the fact that they actually block any inherent activity related to the GABA receptor to the receptor. So, for instance, um, the GABA receptor by itself has inherent activity, and that means the level of activity that is there even in the absence of a messenger. So those receptors are in equilibrium. Um, you have active forms of the receptors and you have inactive forms of the receptors, and they are all in equilibrium. So for instance here, you have different conformations, right? So this is the inactive conformation and this is the active conformation. So the agonist actually is going to be able to bind, and so you have inactive conformation here, and this is the active conformation. So the binding site of the agonist is here when the receptor is actually active. Now, in the when you add an agonist, the agonist is going to push the equilibrium of the receptor towards the active conformation. Okay, it's going to push it towards the active conformation. So in the resting state, you have some receptors in the inactive conformation and some in the active conformation. When the agonist binds or in the presence of the agonist, it's going to move the equilibrium from the inactive conformation to the active conformation. Now things are different when antagonists bind. When the antagonists are present and they bind, they're going to move the equilibrium from the active to the inactive. Okay, they're going to move it in this direction. When you have an inverse agonist, the inverse agonist is going to cause. There's actually an image that is missing here for the inverse agonist. So the inverse agonist is actually going to suppress even the intrinsic activity that the receptor has. Okay, and then addition of the partial agonist. The partial agonist is going to have um, both the active and the inactive in equilibrium again. So you're gonna have to really look at almost like looking at comparing the agonist activity versus the antagonistic activity. And a partial agonist um, can have activity at some, let's say at some subtype, it is agonists, and at some subtype of the receptors, it works as an antagonist. Now, so if you look at the different A, B, C, D here that we've looked at, okay. So let's say this is at the resting resting state. Okay. Now, if you have an agonist, I should say this is a dose response curve where you have the response on the y-axis and the dose of the drug on the x-axis. An agonist will give you these types of response. A partial agonist will give you a response that is not as strong as a full agonist, but will give you some response here. Then this will be an antagonist. The antagonist will in the presence of the antagonist, you will not see activity. Now the inverse agonist is going to show you these type of activities here. So given a particular molecule, you should be able to, looking at the dose response curve, you should be able to tell which one is an agonist, which one is a partial agonist. which one is an antagonist and which one is an inverse agonist. Okay. Now I have not given you the actual data to be able to plot these curves, but it is possible that I can give you the concentration of the drug. Let's say I give you concentration of drug and I give you percent response, okay, in a table format. Table format. Okay, and then we generate these curves, and based on those, I could ask you to let us know which one is which one is the agonist, partial agonist, antagonist, or inverse agonist. Now, the concept of desensitization and sensitization is important, especially when it comes to um, drug of abuse or using a medication for pain. Receptors can become desensitized if they're being exposed for a long time to a particular agonist. And looking at this image here, for instance, you have an agonist that's going to come and bind to the receptor. Because of the presence of the agonist, the ion channel is going to open. But this agonist has stayed in the binding site for so long that after a while, you are going to actually see phosphorylation and then closure of this channel. Now, the process of sensitization happens when the receptors um, have been sensitized over a long period of time because they've been exposed to an antagonist. Okay, so when the antagonist is present for a long period of time, the cell is going to then order the synthesis of more receptors to make up for all the receptors that are blocked. So then the cell is going to be more sensitive to the natural messenger again, which will lead to either tolerance or dependence. Let me show you the image here. So when you have more receptors to block, then now you need a higher dose of antagonist than you needed before to achieve the same effect that you had previously. So the cells become super sensitive. Now, what happens when the person decides to stop using that antagonist, stop using that drug? Now you have a high number of receptors that are available and nothing to block them. So the cell becomes super sensitive to the presence of the normal agonist, and it becomes people have withdrawal symptoms, withdrawal syndrome in these cases. So let's look at sensitization again here in image. It's always better to have these illustrations. So you have a neurotransmitter that will normally bind to its receptor here and cause a normal response. Okay. Now, in the presence of an antagonist, that antagonist is going to bind to the receptor and block the natural neurotransmitter from interacting with its receptor. Cause no response. As a response, the cell is going to synthesize more receptors, and this is what we call sensitization. So because all of these receptors were blocked, now the cell is going to synthesize more receptors. Now, in order to have the same effect, you need to have more neurotransmitters. You need to take more neurotransmitters to interact with these cells, to interact with these receptors. So you're gonna have you're gonna need more antagonists to block it. Okay. So you have to increase the amount of antagonists that you were taking. So that's the process of tolerance. This is how tolerance takes place. So again, sensitization is when the antagonist is introduced, it blocks all the receptors. Then the cell decides to synthesize more receptors so that the natural ligands can still interact with the receptors and cause a response. Okay. Tolerance. Tolerance happens when now you need a higher dose of antagonist to get the same effect that you had before, because now you have more receptors that are open. So then when you stop the antagonist, now you have more receptors that are open, and you become super sensitive to the neurotransmitters that were in the body, which leads to an excess response. And that's when people have withdrawal symptoms, withdrawal syndrome. Okay. And so this is dependence. People are craving whatever drug they were taking. All right, so I want to end this particular lecture here with design of an antagonist for the estrogen receptor. If you remember how the estrogen receptor works, you have a binding site in the estrogen receptor that's going to bind to estradiol. The binding of estradiol to its binding site is going to lead to a dimerization, and the dimerization takes place, but you also have a shielding of the H12 region that's going to come and shield the binding site. Okay, when it comes and shields the binding site, it reveals or it opens the AF2 regions. Opens the AF2 regions. The AF2 region is where the co-activator is going to bind. And once the co-activator binds, this complex here is then going to be able to bind to DNA, leading to transcription. So this is how the estrogen receptor works. Okay. Now, designing antagonists for the estrogen receptor, basically you needed to have a molecule that will bind to the receptor, that will interact with some of the binding regions, but will prevent estradiol itself from binding. So if you look at the phenol and the alcohol of estradiol, they're engaged in key interaction with the receptor, the histidine, glutamic acid, and arginine here. So they're important binding groups. Binding site is spacious and hydrophobic. Okay, spacious and hydrophobic. So inside of the binding pocket, the estradiol is going to orient itself so that its hydroxyl group is going to be pointing up, and the phenol is going to be pointing down here. Okay. So this allows the molecule to be oriented inside of the binding site, and estradiol acts as an agonist. Now raloxifene is going to get inside of the binding pocket. Now it still has hydroxyls that are going to mimic the alcohol and the phenol group of estradiol. So it will come in and it will orient the molecule in a similar way. However, raloxifene has a side chain that estradiol does not, and that side chain is going to be able to interact here with the aspartic acid 351. And that key interaction here, is what's going to allow this molecule to have its antagonistic activity. So raloxifene is going to be an antagonist. The phenol groups mimic the phenol and alcohol of estradiol. Again, the interaction with aspartic acid 351 is important because it prevents the receptor helix H12 from folding over as a lead. And because it doesn't fold over as a lead, the AF2 binding region is not revealed. So you cannot have the binding of the cofactor. You cannot form the complex that's going to bind to DNA to lead to transcription. Okay? All right, hope this was helpful. The notes are posted as well. Go ahead and read through the material, and if you have any questions, feel free to send me an email about it, okay?